Thank you for the introduction. I'm Federico Cerruti from Cardiff University, and this is a joint work with many colleagues from Cardiff itself, but also UCLA, Army Research Laboratories. Our colleague is sitting just at the back. And colleagues also from Turkey, Ozesian University. And first of all, I'm recording my voice, but don't worry, if there is any question, I will just cut the voice of the audience. And this is also linked to the dais-ita program, so you're going to see a lot of times this logo today. Essentially, I'm going to talk about a possible case study. And let's suppose that you are in charge of developing an alarm system that should be triggered when detecting a flying drone and a human at the same time, and using a video stream, right? And this is in the context of collective situational understanding, just because, as we will see, you might have that information might be processed by different entities. And you might have some requirements, like you might have requirements regarding input data efficiency, in particular reliability, because while training on large data sets on when something might be a potential issue or when something is going to be a potential threat is potentially unfeasible, because hopefully threats are less likely than normal situations. High accuracy in analyzing the video stream, that is potentially straightforward. As robust as possible to open set classification problem, in the sense that, as we will see in a few slides, there might be unknowns that you have to face in dealing with these situational understanding tasks. And the idea is that although we are not yet there, whether we can automatically derive this system from a combination of different components in an automatic fashion. So essentially, the question of today is how we can classify AI systems for automatic composition. And the first thing that we can think of is to have a sort of principal analysis of what are the capabilities of each of those AI systems, and essentially how we can measure some properties of those systems. So we can start dividing properties in terms of structural properties, economical properties, or quality assurance properties. And on the structural, clearly the learning typology is fine. Usual classification in terms of supervised, semi-supervised, and reinforcement learning. Society typology, whether you are considered a single agent, multiple agents, and when you have multiple agents, which type of typology are you considering there? Economical is whether you are input data efficient, whether you can tell additional piece of information in your learning set, but also parsimony of the learned model. Sometimes you have to deploy perhaps a model on a limited capability device or mobile device or other aspects. So that might be also linked to the economic aspects of the system you are going to use. And then quality assurance, that clearly can be very much linked to the type of task you are dealing with. That might be clearly inferencing accuracy, fine. Confidence representation, not just telling you what, if you are a classification task, which class the object belongs to, but also which sort of range of confidence. Robustness can be against many aspects. I think we are going to have a talk later on from Simon on robustness against adversarial examples. You can have robustness against open class problems. And then reasoning capabilities, in the sense that you might not just want to do a simple classification task. You may want to have additional reasoning on top of that. So if we go back to our requirements, then we essentially should first map those requirements into some desideratum elements of these properties that we saw before. So for instance, input data efficiency clearly maps directly with input data efficiency, fine. Accuracy in analyzing the video stream, again, is relatively fine. Robustness possible to open set classification goes back to this robustness I was mentioning before. So if we now take our case study into a sort of real-world kind of scenario, we can say, well, you might have some vendors giving you some capabilities, but it's very unlikely that you can derive a new capability just for this new task. You might want to compose your capabilities from different vendors. And this is also argued in the influential paper on robust AI by the former AAAI president, suggesting that perhaps you want to have an approach that is having as many as components as possible that can be interchangeable, and you can play with that. But in this situation, let's suppose that you have a convolutional neural network, fine. A potentially subjective logic Bayesian network, or in any case a Bayesian network, a probabilistic logic programming system, and LGA topic modeler system. And clearly we know that CNN are not particularly input data efficient. They are pretty good for object detection accuracy. They are not robust much against open set. And we don't know about their expressiveness in terms of symbolic reasoning, although there are some neural networks are allegedly to be Turing complete. Regarding Bayesian networks, we know that input data can be very efficient. Is not very good idea for using for object detection accuracy, and not good for robustness against open set. Symbolic reasoning is essentially analysis of probabilistic inference over propositional logic knowledge base. Similar for Problog, where we move from propositional logic knowledge base to a subset of a first order logic knowledge base. We will talk about Problog towards the end. LDA is the nice thing of LDA is that it's quite robust against open set classification because it's a unsupervised machine learning system. So let's suppose that okay, we need to design this alarm system, and we know that if you have a drone and the drone is flying, and let's suppose that you detect also the human, then you are in danger, right? So you can have your usual, a very simple Bayesian network, and let's suppose that these numbers, because it's relatively rare situation that you are going to be in danger in front of a drone flying with a human, then those numbers are derived by some experts. So let's suppose that now we are playing with this situation in the real world. We have, unfortunately, this is the only picture I found with Creative Commons license and picturing a gentleman and a drone. So in this situation, then essentially you would like your alarm system to be triggered, right? But what can happen is that, apologies for the low resolution of the VGA, so the CNN can identify the person with 93% of accuracy, but now you have that there is this violet box that is a traffic light with 34%, and this yellow box is an airplane. And the reason for this one is that the CNN doesn't have the concept of drone, because perhaps your vendor was 10 years old and did not update the training with the concept of drones. In this case, it's just object detection API in TensorFlow with Mask CNN with ResNet 101 model trained using common object in context datasets. So in this dataset, there is no concept of drones. Fine. So this is one of the cases of open class classification problems, where what we can do is try to say, well, we know that this is an airplane. Well, we can do the same for traffic light, but that is uninteresting. We know that there is an airplane. Well, what is the global knowledge base of the mankind is Wikipedia, clearly, and we can just run topic modeling on Wikipedia. We ended up with some topics like wing, aircraft, plane, flight, engine, and if you can just then do some semantic matching between those concepts and concepts we know from the Bayesian network, then we can end up that this flat and this flying might have some similarities. That can be done using some WordNet type of analysis. And if you then use this one as evidence that something is flying, although you don't know that it's a drone, then you might end up with danger, which is essentially sort of a sort of argument in favor of, if you want to design something like this, try to be as robust as possible, because you might have evidence for something but not for the entire world. But this is also an argument for something more, to use something more expressive than just Bayesian networks or something like that, which is perhaps why aspects related to probabilistic logic programming, or in general uncertainty over a first-order logic kind of knowledge base, can be very useful. So first of all, ProbLog, like many other approaches, can encompass Bayesian networks. It cannot encompass subjective logic Bayesian networks because they did not extend it yet, considering from simple probabilities into beta distributions. But essentially what you have here is that is a knowledge base in logic programming. Those are antecedents. This is the conclusion. And this is the probability of this rule to happen. And if you have just something like this, is the a priori of flying, like 0.5. And this one is not flying implies drone is 0.5, flying implies drone is 0.7, etc., etc. Fine. But this is still propositional. What you can also do is start saying, well, the reasoning that is behind the linkage between LDA and the connection with what is stored in a Bayesian network can be also encompassed by using a logic program. Very simply, by just saying, well, if we just observe something that is an airplane, and this airplane might have some connection with flight due to this LDA, flight can have some connection with flying, etc., etc., and then you ended up with some posterior probabilities that this object is actually flying, and that might be linked then to the Bayesian networks. But in general, this shows that you can actually reason not just with propositions, but also with variables and with types of objects. And that it can be clearly expand further to encompass all your set of capabilities. So you might have different sensors, different objects flying at the same time. You might want also to express closeness of objects together. You can definitely expand your ability to reason about the situation in this way. So to conclude, this is clearly a very early stage, and we are just scratching the surface of what might be necessary to enable better human-machine teaming for situational understanding. We believe that principal critical analysis of AI techniques can support some of those tasks. These might give us the ability to derive guidelines for deriving distributed systems for collective situational understanding. And this is essentially a case study for advocating for compositional distributed systems for situational understanding. Thank you very much for your attention.